A capacitor, often simply called a cap, is not complicated. As long as you understand that opposite charges attract and like charges repel, it becomes easy to understand. A capacitor consists of two metal plates. Under normal conditions, the plates are neutral, meaning the number of positive and negative charges is equal. When we connect the capacitor to a power supply to charge it, the positive terminal attracts the negative charges on the upper plate and pulls them away from the positive charges. At this moment, the upper plate has more positive charges than negative ones, so it becomes positively charged. After reaching the power supply, these electrons are repelled by the negative terminal and move to the lower plate, which then becomes negatively charged. As more electrons are pulled away, the positive charge on the upper plate becomes stronger. Due to the attraction between opposite charges, the plate starts pulling back the electrons being taken away. However, the power supply's attraction is stronger, so the electrons continue to move away, but more slowly. Eventually, the positive charge on the plate becomes strong enough that the electron experiences equal forces from both sides and stops moving. At this point, the system reaches equilibrium. Now the two plates hold opposite charges, and the voltage across the capacitor equals the supply voltage. The charging process of the capacitor is complete. Now let's look at the current curve during the charging process. Right after connecting to the power supply, electrons move the fastest, so the current is at its maximum. As electrons experience forces from both sides, their movement slows and the current gradually decreases. When charging finishes and electrons stop moving, the current becomes zero. Now let's examine the voltage curve across the capacitor. At the moment it is connected, the voltage is zero. As the charge difference between the plates increases, the voltage gradually rises. Eventually it reaches equilibrium. This is the charging process. Now let's look at discharging. When a charged capacitor powers a light bulb, the positively charged upper plate attracts electrons from the lower plate. As electrons move, the voltage difference between the plates decreases. The movement slows down, and the bulb becomes dimmer. Finally, the voltage difference becomes zero, the bulb turns off, and the discharge ends. This is how it appears on the graph. After the bulb is connected, the discharge gradually slows until it eventually reaches zero. With this understanding of charging and discharging, we can easily understand some capacitor characteristics. First, the voltage across a capacitor cannot change instantly. If the circuit uses a resistor, the voltage across it instantly becomes the supply voltage when the switch is closed. But for a capacitor, the voltage rises gradually instead of changing instantly. Another very common application of capacitors is filtering. For example, in this circuit the resistor normally has a stable 5 volts across it. If the power supply experiences interference, the voltage may suddenly spike. The voltage across the resistor will show the same disturbance. The voltage waveform will show sharp spikes. If we add a capacitor across the resistor, these spikes can be filtered out. How does the capacitor achieve this? When the voltage suddenly increases, it is equivalent to charging the capacitor. If the spike lasts long enough, the capacitor voltage will eventually reach the same level. However, interference spikes are usually very brief and quickly disappear, so the capacitor immediately begins to discharge. Even though the supply voltage changes sharply, the capacitor smooths it into a much smaller variation. This is the principle of capacitor filtering.